Hey AP Chemsters, this is Mrs. Vanderwall bringing you the 15.4 edition of Blankwalle. I'm back. Anyway, so today we're going to be talking about acid strength and acid ionization constant. Ooh, there's that K value again. Remember that from chapter 14 from equilibrium. It comes back again. So anyway, before we begin, I just want to remind you that good note-taking idea would be if there is something that you want to jot down, maybe a definition that I'm not writing things down on, but maybe you want to jot it down yourself, feel free. You don't have to write only what I put down on here. You're free to write down anything that will help you study your notes and review for the tests and the big AP test in May. So, write anything down that will help you, okay? And that is helps you focus more, and it's good strategy for your future for when you're in college. So enough of that. So let's get started. Let's talk about acid strength. So it says the strength of any electrolyte. Well, let's just pause right there. What's an electrolyte? Well, it's anything that in solution will conduct electricity. Ooh, clever title, isn't it? So what are things that will conduct electricity? Anything that has an ion in it. And in this case, for this chapter, we're talking about acids. If you recall, acids are proton donors, which is an H+. There's your ion. And bases are your proton acceptors, typically a negative charge. So we have ions in solution, and they will conduct electricity. So let's go back to the beginning. It says the strength of an electrolyte, in this case acids, depend on the extent of its dissociation. Well, what does dissociation now means? Well, think about what the word dissociate means. It means to basically split up. So if you and your BFF have an argument, you may dissociate from them. You split up and you're not talking for a while. Hopefully you get back together again though. So the strength of electrolyte, in this case acids, depend on the extent of its dissociation, how much it splits up into its component ions in solution. Keep in mind, what do acids do? They donate the proton. So how much will the acid give up its H+? How much will the base accept the H+? So that's how this acid strength will be determined. So it says a strong electrolyte dissociates completely into ions in a solution. What does that word completely mean to you? It means 100%. It means all. None left over, all right? So all means all here. So a strong electrolyte will completely, 100% of the times, dissociate into the ions in its solution. So the example is HA, so that is your strong acid in this case. In water, again it has to be in water, will dissociate into A- and the H3O+. The A- is the conjugate base and the H3O+ is the hydronium ion. So what do I have right here? Notice the single arrow right here. What does that tell me? It tells me that it's a strong acid. Write that down. A single arrow is a strong acid. So the question now is this going to be in equilibrium? Well, what do you think? The answer is no. It is not in equilibrium. Why not? There is no reverse reaction. If you have a strong acid right here, it will 100% ionize into A- plus H3O+. What does that mean? The A- will not grab an H+ from the hydronium and recreate this again. It won't work. Okay? So what about the opposite of a strong acid? What about a weak acid or a weak electrolyte? Will dissociate partially. Well, what does that mean? Not 100%, not all of it. Some of it will stay intact. Only some of them will split up. So a weak acid will partially ionize. And what are you going to notice here? Notice you have a double arrow. What does that double arrow mean? Well, is this in equilibrium? Why or why not? Well, what do you think? Maybe more importantly, what do you think and why? Did you come up with something? Well, this is what I came up with. It is in equilibrium because you do have the forward reaction where the acid meets the water and makes A- and H3O+. But what else happens? That these will come together and make the HA and water back again. So you have both a forward reaction and a reverse reaction. And what did we learn about as far as equilibrium goes from chapter 14? Products over reactants. You can look at the Q, talk about the K. All that is going to come back when we talk about these weak electrolytes, okay? Well, how are we going to know which is strong and which is weak? Well, the good news, and well, maybe the bad news is, there are 6 strong acids. Please, please, please know them by heart, okay? So the 6 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid. So notice those are 3 of the 4 hydrogen halides. And then nitric acid, perchloric acid, and sulfuric acid. We're going to talk a little bit more about why those are going to be strong acids. That's a little bit later on in the chapter. Something about here, you may be wondering, well, look at the hydrogen halides. You're missing HF. Why are you missing HF? And it has to do with all this. It has to do with the bond strength and the acid strength. So what does that chart tell you? Well, the stronger the bond strength, meaning how hard is it to rip that H off the F? It's more energy to take the hydrogen away from fluorine than it is from hydrogen from chlorine, hydrogen from bromine, hydrogen from iodine. So if you look at that, really, the strongest of all these would be HI, but we can't really rank them because all 3 of those will 100% of the time completely dissociate in water. But it's the easiest to break up the HI, okay? So over here it says these 6 acids when placed in water will ionize 100% of the time, and once again this means always. Okay, this means always. So here is the example of HCl plus water. Notice again the single arrow making the hydronium ion and the conjugate base chloride. Okay, so when you put a strong base in water, look what you have. Here's your beginning. Here's your, I'll put the I. Here's your initial or the beginning if you want the B. And you have HCl. But what happens when it hits the water? What's in the beaker now? You have H3O plus and you have Cl minus. Okay, 100% of what goes in splits up. So it says draw a picture below when HI dissolves in water. All right, so here's my beaker. Okay, lovely beaker, I know. And I'm going to pour in some HI. Hi, here's my water. Okay, what's going to happen? You finish off the picture. All right, did you get, I'm going to just write H plus instead of hydronium, it's easier, and I minus. They all will split up, okay? That is a good picture, and it's a really important picture. Remember, the AP folks love these kind of diagrams here, so really understand what's going on. Okay, let's turn to the next page. So now we have weak acids, which do not 100% dissociate. And we can actually rank these weak acids from strong weak acids to really, really weak acids. And they will not 100% ionize in water. And the more it ionizes, the stronger the acid. So the more to the right this equilibrium will shift, the stronger the acid will be. So again, we have the double arrow here, which is super important. And notice we said that HF was a weak acid. It does not 100% dissociate in water. So here's our picture of HF. So you put HF in, you have some HF, some F minus, and some H3O plus. Notice you have all 3 species in the beaker. And again, here is our picture from the molecular level. So how about this one, HCN? So draw a picture. Here's my water, and I'm going to dump some HCN in here. Okay, and show me what it looks like. Now, wait a second. How do you know that HCN is a weak acid? Do you have an answer? How about this? What is HCN? Is it hydrocyanic acid? Make sure you know how to name that. Is hydrocyanic acid on the list of the big 6? The answer was no, it is not. If it's not on this list right here, well, guess what? It's weak. Any other acid is going to be considered weak. So hydrocyanic acid is, and it was also weak acid. So go ahead and draw your beaker now. did you do this? I have some HCN, some of it stays together, and some of them will split up. Well, what will some of the H plus and CN minus do? Oh, they'll also come together and form more HCN. So then some HCN will split up to form H plus and CN minus. So at equilibrium, the rate of the forward reaction of splitting them up is equal to the rate of the reverse reaction of coming back together again. So it says the degree of ionization depends on the degree that the acid is weak. Okay, so what the heck does that mean? Remember, this is in equilibrium. Okay, so we can talk about the forward and the reverse reaction. Okay, we can talk about K values here, like we could with the equilibrium we learned in chapter 14. So what does this say over here? The degree to which the reaction proceeds in the forward direction to the right depends on the strength of the attraction between the H plus and the A minus. If the attraction of the H plus and the A minus is weak, it favors the forward reaction. So you're going to make more products. So what would K equilibrium be? If you said the K equilibrium is greater than 1, you're right, just like what we did earlier. So what if the attraction between H plus and A minus is strong? It favors the reverse reaction. So what will the K equilibrium be here? It'll be less than 1. Okay? The stronger the acid, the weaker the conjugate base. Make sure you got that, okay? So we're getting a little bit of foreshadowing here. We had the Kp and the Kc. Now we have a Ka. All right, and that's your acid dissociation constant. So here is our equation. So the K value, once again, the law of mass action is right here, where you have the concentration of the H plus times the concentration of A minus over the initial concentration of HA. So again, it says H3O plus and H plus are going to be the same thing. Why is water not included in the Ka expression? You remember why? Because water is a liquid. What's the only things you put in these equilibrium expressions? Either gases or aqueous. We're not going to talk about gases in this chapter, so everything we're going to do is going to be aqueous with a concentration of the molarity. Okay? So the acid dissociation is the same thing as saying dissolving the acid in water. It's aqueous. Okay? So problem number 6, what is the acid dissociation constant for the generic reaction here? Why don't you go ahead and pause this and write it down yourself. If you got that, you're doing great. So once again, we said H3O and H plus are the same thing. I prefer to write H plus. It's easier. Okay, now let's do problem number 7. Write out the simple dissociation ionization reaction. Again, you can omit the water for each of the following acids. Then write the acid dissociation expression. Well, hydrochloric acid. Uh-oh. What do you know about hydrochloric acid? Does it ring a bell? Is it one of those big 6? Look at this. Okay, so let's think about this one. If we had 100% ionization, so no matter what my initial concentration is, guess what? We're going to use it all up and be 0. So what would this be? So K would be your products over reactants. And what if your reactants ends up at quote, equilibrium, 0? Well, what's K going to be? It's infinity, isn't it? So you don't have a K dissociation expression because K is infinity. So what about acetic acid? Let me erase this for a second. Well, in order to do these next problems, you have to know what acids they are, and acetic acid is not one of the big 6, so it is a weak acid. Notice I have the double arrow, and it splits up. So here's my acid dissociation constant. I have products over reactants just like before. Why don't you pause and do your own chlorous and hydrocyanic acid? Well, here are my answers. Hopefully you got the same thing. You should be doing great. This is the law of mass action, just like what we used before. And also notice that everything's a concentration. You don't have to worry about pressures. So let's look at problem number 8. And it says, consider these two acids and their Ka values. Which one is stronger? Well, what does that mean? Which one will produce more products? Think about it. All right, the one that has the greater Ka means it ionizes to a greater extent and it has a greater value. More products, less reactants. Don't wait to be